fit a line, you'd probably say, well, that's the correct line, that line that kind of goes through most of the points and somehow ignores that bad point. You're going to say, aha, that's right. Remember evil Megan? That was the evil Megan point. The problem is, if we don't know that that's an evil Megan point and we actually include it in, say, our least squares fit, we were showing you that our best fit line was not such a good one. And really what's happening, before we talked about robust estimators, what's really happened is you're just not going to get points like that from a Gaussian distribution. That is such a low probability. That point comes from outside our model. And so we have to figure out somehow that it's one of these outliers that's outside of our model. So here's the main idea of this algorithm called ransack. Fitting a line, a model, is easy if we know which points belong to that model and which do not. At which point I wrote, duh, yeah. A little more interesting. Now, if I had proposed a particular model, a particular line, we could probably guess in a whole bunch of points which of those points come from that line or come from that model. And those are called inliers. That is, they come from the model. The algorithm random sample consensus works as follows, and we're going to go through this. Randomly pick some points to define your line or your model. Okay? Then repeat this enough times until you find a good one. And what does it mean by a good one? A good one is one that has many inliers. That is, a lot of points are from that line. And you might think that this is a hopeless idea, just randomly picking things and computing them and hoping that you can get. Well, it turns out, actually, as was shown by Fischler and Bowles way back in the dark ages of the universe, 1981, that actually this copes with a very large proportion of outliers very well. I'll also tell you that Marty Fischler was my first boss after my PhD, and Bob Bowles sort of taught me the ways of the force or of computer vision after 1981, but not that many years after. Any given model type, so whether it's a line or transform, they have what's known as a minimal set. The minimal set is the smallest number of samples from which the model can be computed. So for a line, how many points is that? Well, 2, all right? But what about transforms, when we're transforming one image to the next, okay? Image transforms are just models. So what is the minimal set of our different transforms? Well, first of all, what are we sampling from? Well, we're sampling from proposed matches, corresponding pairs of points, okay? So suppose I think that one image is just translated of another image. So the transformation is a translation. How many pairs do I need? 1, because if you tell me where this point A is in this other image, I now know the translational shift between any 2 points. Another way of thinking about that is I need a delta x and a delta y, and you give me an x and a y match. So I know what delta x is. I do this complicated thing called subtract, and I do it on y, and that's my offset. Okay. Homographies. Ooh, we talked about this. How many pairs of corresponding points do we need to compute a homography? Do you remember? Paying attention out there? 4. Megan, get it right. How about a fundamental matrix? We showed you something called the 8-point algorithm, right? That said if you had 8 points, corresponding pairs, you can compute that. By the way, it's actually 7. We didn't really talk too much about that. Do you remember when with 8 points we could solve for the fundamental matrix, but then you would sometimes end up with a rank 3 fundamental matrix, so you had to reduce it down to a rank 2. So we did that whole getting rid of the smallest eigenvalue. That's because there's actually fewer degrees of freedom. So in principle, you can do it with 7 points, but we're just going to think of it as 8 points. So the idea is, for a translation, I need 1 pair. For a tomography, I need 4 pairs. For a fundamental matrix, I need 7 or 8 pairs. This is the minimal set that it takes to compute these things. Then you can write down the general ransack algorithm. Randomly select, it says S points, or point pair, S elements of a sample set. So you form a sample by pulling out S things that you need. You instantiate your model, so you either draw your line or compute your homography, whatever it is you do. And then you get a consensus set, C sub I. And these are the points that are sort of within the error bound. So if you think of it as homography, homography maps this image to that image. And I can see, are the points that are all these points mapped, how many of the proposed matches now land in the same place that they said they came from? That's the number of inliers. And In fact, you might even terminate this algorithm as soon as that consensus set is big enough, or you might just repeat it for n times, and then you return whichever model gave you the biggest set. So that's the general ransack algorithm. And of course, like any other algorithm, there are some parameters to be chosen in order to make this thing work. So the first parameter is this number s, the minimal set. That's how big is the minimal set. That number is actually usually set by whatever model you're using, right? So if you're fitting lines, that number is 2. If you're doing homographies, that number is 4 pairs. So that's set by the model. A little more problematic was this distance threshold t, or delta, as I wrote in the Greek, of saying how far away from the model that you're computing is acceptable to be an inlier. So let's look at that one just a little bit. The bottom line is, in order for you to pick a threshold, if you wanted to do this sort of analytically, what you need is a noise model. And unfortunately, this noise model is not the same model as the thing we were doing before. It's not our line, it's our belief. I'll use the word belief maybe instead of model. No, because it's a model. It's a model of how we think the noise behaves. So let's go back to our line example. You remember this? So if we were just looking at a line, so let's assume that we have this real line and that our points are perturbed by a Gaussian noise. This is the thing we looked at last time. So the distance in a Gaussian is sometimes a complicated thing. So if you have a multidimensional Gaussian, you may know about chi-squared, and and the square root of that is the distribution of the distances. In 1D, it's actually much easier. It's essentially what's called a half normal, because basically, the probability that you're d away is you can either be d this way or d that way, but d is only a positive value, so it's just twice the regular Gaussian distribution. That's what this distribution here looks like, because it says d greater than 0. All that matters is, given a noise model, you could generate a distance model. And given a distance model, you could pick a threshold. So in fact, if you have this 1D Gaussian, let's say, and let's suppose it has a distribution parameter of sigma squared, then you could set the threshold t based upon t squared. Is this number 3.84 sigma squared? Where the heck does 3.84 come from? Well, I just arbitrarily said, let's pick a threshold such that 95% of the inliers would fall within that threshold. So 95%, if you got sigma squared, then I set t squared at 3.84 sigma squared. If you wanted 99%, you'd have to make it a bigger threshold. If you're willing to remove some points, you'd make it a smaller one. But the idea is that you have some threshold, and then you're going to accept the point if the distance d is less than that threshold. You'll count that point as an inlier. Okay? Cool. All right, so let's see. We've got our number of points. We have our distance threshold t. It says what we did here before. We've got one more. The number of samples we're going to compute. Now, this is not S, the number of points within a sample, right? A sample is a set of points that it takes to compute a model. This is how many times are we going to draw a sample? How many models are we going to try and check? So what we'd like to do is we'd like to choose n to be big enough that we can't actually guarantee that we're always going to get inliers, can we? Right? Because if we're randomly picking points, etc., and unless we would exhaustively pick all, say, n choose 2, if we're just randomly picking things, it's only with probability that we can say that what's the likelihood that we got a good solution. So what we're going to do is let's pick a probability p, and what we want to know is how big does n have to be such that the probability is p, let's say 0.99, 99%, that at least one of our samples will just be made up of points that come from the correct model, right? So that's a way of saying it. If this line, I actually get 2 points that really came from the line. Or another way of saying it is, I've got all these putative matches that are and I want to compute a homography. I want at least one set of 4 matches that I test to actually be the correct homography, all right? So the question then is, can we figure that out? And in particular, it should be pretty clear. What if all the points were right? That is, all the matches were right. Well, then as soon as you pick some set of 4, you would have 4 points that are correct, and you'd get the correct homography. What if none of the point matches were correct? Well, then you could be there all day, and you're never going to get 4 that match. In between those is that there's some percentage of points that are not correct. So if the ones that are correct are called inliers, what do you think the ones that are not correct are called?
Outliers.
Outliers. So the question is, for a given percentage of bad points, for a given outlier ratio E, so E is 20%, means that 20% of your points are bad. For a given ratio, how many samples do we have to check? So what we're going to do is we're going to calculate N. And it's actually really easy. You just step right through it. So we start off with S. S is going to be the number of points in the minimal set. Okay? P, the probability of success. This is, I want to have probability of P that at least one of my samples will be a correct set of points. Now E, we said before, is the proportion of outliers. So what's the proportion of inliers? Well, if the proportion of outliers is 20%, the inliers is 80%, just 1 minus E. Okay? All right, now we start with just a little bit of combinatorics. All right, so let's suppose I pick S of these things. What's the probability that they're all inliers? Well, if the probability of being an inlier is 1 minus E, the probability that they're all S are inliers is 1 minus E to the S. I'm assuming that there are a lot of points to choose from, so that the fact that I've pulled one out doesn't diminish things. It's a pretty good approximation. Okay, so that's the probability that all of the points in the sample I pulled are inliers. So what's the probability that at least one of those is an outlier? Well, 1 minus that. Okay, so that's just 1 minus E to the S. Okay, so if I pull out N sets, what's the probability that all N are outliers? Well, given that my sets are independent, so it's just this 1 minus E to the S, all raised to the N. Okay, so that's the probability that all N samples have an outlier. Okay, but of course, what we want is the probability that all of them are outliers. So that means they were all bad. We want that probability to be really small. That is, less than 1 minus the probability of the success. So judging here, right, so if P here was 99%, 1 minus P would be 1%. We want the probability that they were, all of our samples had at least one outlier in them. We want that to be less than 1%. So that means that we can now just substitute in, and we get this ugly expression, 1 minus E to the S to the N has to all be less than 1 minus P. Drum roll, please. We can solve for N, and bingo, there is our equation. N's got to be greater than the log of 1 minus P divided by the log of 1 minus E to the S. And I'm sure you all have deep intuitions for what that looks like. No? Okay, let's look at some representative values. So here it's just a table, and I've highlighted a couple of entries. Let's first take a look at S equal 2 here. So let's suppose we were doing fitting a line, or if we're doing a transformation, that's a similarity transform where you take 2 pairs. Notice that if my percentage of outliers is 50%, so half my matches are bad, I only have to choose 17 examples for me to have a 99% chance that at least one of them was the correct one. So doing something 17 times in a computer like that, that's pretty fast. If I'm computing a homography, S is now equal to 4. Even with 50%, I only have to try 72 samples. So even though I'm totally randomly pulling these things, and I have no idea which points are right or which ones are wrong, and half the matches are wrong, with just 72 of them, I have a better than 99% likelihood that one of my sets is the correct one. And in fact, even if I'm doing a fundamental matrix, all right, looking for 8 matches, I only have to check less than 1,200 of them in order for it to be likely that one of those matches, at least one, will be a correct set of matches, so the fundamental matrix that I would get would be the correct one. One thing to notice about this table is that N does not go up very much as the percentage of outliers goes up, but it does go up pretty steeply as S gets bigger. So as the number of parameters that you need gets larger, all of a sudden the number of sample sets you have